Periodicity 1. Transition metals, part 1. Essential idea. The transition elements have characteristic properties. These properties are related to their all having incomplete D sublevels. Nature science. Looking for trends and discrepancies. Transition elements follow certain patterns of behavior. The elements, zinc, chromium and copper, do not follow these patterns and are therefore considered anomalous in the first row D block. Let's look at some of the physical properties. Melting points. They're high. They're high because they have strong metallic bonds. Malleability and ductility. The transition metals can easily be beaten into new shapes and can be drawn into wires. Ductility is the ability to draw into a wire. I've got a high density because it's got small atomic radius. They have a high tensile strength. They can hold large loads without breaking. And have a high electrical conductivity because they've got a large number of delocalized electrons in the 4s and 3d levels. The chemical properties. They have variable oxidation numbers. For example, copper has an oxidation number of 1 or 2. Iron, 2 or 3. Manganese has 7, 4 or 3, and others. Compounds, they're often coloured, and their ions often form complex ions, which we'll talk about later. You can see 2 examples there. The copper there has got 6 water molecules bonded to it, and copper there has 4. And these are ions, they both have a charge. Magnetic properties, well, iron's probably the best example that you know of, and it's a transition metal. It's what most magnets are made of. And they have many uses as catalysts. For example, magnesium oxide is used in the decomposition of hydrogen peroxide, and iron is used in the Haber process where we make ammonia. And transition metals are found in the D block, and we've got a list of there going from scandium to zinc. You'll notice zinc is in yellow. Let's have a look at their electron configurations, and we've got argon as the root electronic configuration for this lot, and then scandium has a full s orbital and 1 electron in its 3d orbital, and we'll just add as we go along until we get to chromium. And if you remember, in chromium, one of the s electrons moves into the d orbital, so it has a part, so it's half filled basically. Manganese has a half filled at the orbital too. We'll go through adding one at a time. And again, copper is a bit different because one of those s orbitals goes into the d orbital. One of the s electrons, goes into the d orbital. And zinc is full. So let's have a look if we draw the orbital box diagram. You can see both chromium and manganese are half full. Then iron is the first one with a pair of electrons. And then both copper and zinc have complete d orbitals. The electron configuration for transitional metal ions, you should already know this, we've been through this before. This is kind of a recap. So iron has outer electron configuration of 4s2, 3d6, and as we know, we'll lose those s electrons, giving 3d6 for iron 2+, and we'll lose 1 d electron to make iron 3+. In titanium atoms, we're going to lose those 2s2, so we're going to get 3d2, and then it can lose 2 more to make a stable noble gas configuration for titanium 4+. And copper can lose that one electron, because remember it's already given one s electron to the d orbital. You can lose that one electron to get a full d set, and it can also form copper 2 plus, which would be 3d9. Remember, we do always remove the outermost electrons first. In this case, it would be the 4s electrons. Zinc and other elements in group 12 are not considered to be transition metals. The current IUPAC definition for transition metal is as follows, quote, an element has an atom with an incomplete d sublevel, or that gives rise to cations with an incomplete d sublevel. So zinc atoms have a full d sublevel, and so does its cation. Okay, so it's not considered a transition metal. Scandium used to be considered, scandium used to be not considered a transition metal, and you might still see that in some textbooks, revision guides, etc. But some new compounds with scandium 2 plus were found, and they have an incomplete d orbital. Let's have a look. Transition metals can form several several stable cations with different charges. You have a look at these. Do remember that there should be 8 plus 2 here too now, because of those recent findings. So all the transition metal ions have an oxidation number of +2, and if you think about it, that's obvious because they're coming from those the 4s electrons are being lost every time, and then it varies a little bit. Let's try and write the electron configurations for V5 plus, cobalt 3 plus, and chromium 2 plus. So vanadium has a 4s2 3d3 in its outer electrons, and it can lose all 5 there to form the stable V5 plus, which has the stable noble gas electron configuration. Cobalt 4s2 3d7, so we're just losing 3 here, so we're going to lose the s1s first and one of those d electrons to give us 3d6. And chromium 2, we're going to lose that s electron and one d electron, which will give us 3d4. So why do transition metals have variable oxidation numbers? Let's consider these successive ionization energy values in kilojoules per mole. Calcium is in the S block. After the 2 electrons in 4s are removed, the ion has a very stable noble gas configuration. There's a large increase from ionization energy level 2 here to ionization energy level 3. So removing additional electrons is not energetically favorable. Conversely, in titanium, which is in the D block, after the first 2 electrons in 4s removed, the energy required to remove the 2 electrons in 3d is not so much greater. It's possible to form Ti3 plus and Ti4 plus. Removing the 5th one over here though is unlikely because it has a much higher energy demand. You would be removing it from the stable noble gas configuration. So have a go at answering these yourselves. Press pause and give it a crack. Okay, so we're going to explain why manganese can have an oxidation number of +7 but chromium cannot. Well, that's manganese's electronic configuration, and you can see straight away it has 2 s electrons, 5 d electrons, so 7 outer s and d electrons, which it can lose to form manganese 7 plus, which will have electron configuration of the stable noble gas configuration. But chromium only has 6 outer s and d electrons to lose, which will give it the chromium 6 plus, and then it will form the stable noble gas configuration, and then it's unlikely to lose more electrons to form stable ions. In the same way, vanadium here has 5 outer sd electrons, which you can use to form vanadium 5+, which will have the stable noble gas electron configuration. So complex ions, we said transition metals form complex ions. What are these things? A complex ion is one where a metallic ion is bonded to a ligand via a coordinate dative covalent bond. And what does that mean? Well, a ligand is a small molecule or ion with a lone electron pair that can be used to form a coordinate covalent bond or a dative bond. Some of the common ligands include water, ammonia, the chloride ion, hydroxide ions, cyanide ions. A coordinate covalent bond is one where a lone electron pair from one atom is used to form the covalent bond. Okay, so remember, covalent bonds are where electrons are shared, but you can have sharing where one, in this case a molecule or ion, provides both electrons. The coordination number is the number of ligands bonded to the metallic ion. So you can see this picture, it's got 1, 2, 3, 4, 5, 6. It's got a coordination number of 6. The shape of a complex ion can be predicted using VSEPR. Oops. So this has a coordination number of 6. And we know it's octahedral because it has 6 electron domains. It's got 0 lone electron pairs. This copper tetrachloride, it's got a coordination number of 4. Its shape's tetrahedral. It's got 4 electron domains with no electron pairs. No lone electron pairs. The oxidation state of the transition metal can be deduced. Do note the square brackets around the metal ion and its ligand, and the charge refers to the overall charge on the complex ion. The oxidation number of copper in this first example is +2, okay? And you work that out, it's fairly straightforward. Each chlorine ligand provides a charge of -1, so you're going to have 4 minus, and this gives something plus, so question mark plus is going to equal overall 2 minus, and so obviously this is going to have to be 2 plus to satisfy this little puzzle. Over here, iron CN3 plus, it's got an oxidation number of +3, and let's just double check that. Each nitrile ion has a charge of -1, so you're going to have 6 minus. So what would we add here to get 3 minus? We need to have 3 plus, wouldn't we? So 3 plus and 6 minus gives us 3 minus. So the iron is 3 plus. Next, nickel has a charge of +2. Water does not have a charge, it's neutral, and so nickel must be 2 plus. Let's have a look at this complex ion. We've got 4 ammonia molecules bonding to copper. The copper has a charge of 2 plus. The chemical formula is CuNH342 plus. The ligands are the ammonia ligand. Coordination number is 1, 2, 3, 4. Oxidation of copper, ammonia doesn't carry a charge, and so it's going to be whatever the charge is on the ion, 2 plus. And the shape will be tetrahedral. Now let's have a look at this cobalt, this interesting cobalt ion here. Ligands is Cl minus and water. Coordination number 1, 2, 3, 4, 5, 6. Oxidation number of cobalt is going to be 3 plus. You've got 2 minuses provided by the chlorines here. You've got an overall charge of 1 plus, and so this has to be 3 plus to satisfy that. And the shape is octahedral. You'll notice though, over here, you can have two forms. If the chlorine ligands are next to each other here, it's the cis form. If they are opposite each other, it's the trans form. So you've got some isomers there. We also have monodentate and polydentate ligands, and it has little to do with teeth. There are different classes of ligands depending on the number of donor centers, so atoms with lone electron pairs in the ligand. A monodentate ligand only has a single donor atom that forms a coordinated bond with the metal. So you can see the chlorines here, each chlorine only provides one lone pair to the copper. Here, water only provides one, even though the oxygen atoms do have two lone pairs, only one lone pair is used in the coordinate bond. Conversely, polydentate ligands have two or more donor atoms that form coordinate bonds with the metal ion. A good example is 1,2-ethane diamine. If you look over carefully, you can see each nitrogen atom has a lone pair which is going to the metal. So you get a lone pair from here and a lone pair from there. A single molecule is forming two coordinate bonds or two dative bonds. So there's ethane diamine, there's also ethane diawate, and EDTA, which I think is ethylene diamine tetraacetic acid. And this EDTA is quite fascinating stuff. It can provide 6 donor atoms. It has 6 donor atoms that can form coordinate bonds to a single metal. Let's have a look at that a bit more closely. It's known as a chelating agent. And look at this picture up here. So you've got the nitrogen, an oxygen, an oxygen, and an oxygen all bonding this side. And then you've got a nitrogen and oxygen underneath. Okay, so oxygen, oxygen above would be one way of thinking about it, with like cis nitrogen and cis oxygens over here. Okay, its 6 donor atoms can form coordinate bonds at all octahedral sites, and it tightly holds the metal ion in a 6-pronged claw. Now, these chelating agents have many important uses. They're used in food additives. They remove transition ions that form part of enzymes that turn food rancid, so they can allow food to last longer. Yeah, you can use them to treat heavy metal poisoning. They'll mop up heavy metals. And they also used in water softening. It removes magnesium and calcium ions from hard water supplies. Very useful chemical. Let's have a look at the magnetic properties of the transition metals. Spinning charges, like electrons, act like tiny bar magnets, and they generate a magnetic field around them. When electrons are paired in orbitals, the 2 electrons spin in opposite directions. The 2 spinning electrons produce magnetic fields in opposite directions, so they cancel each other out. The magnetic properties of the elements can be classified as diamagnetic, paramagnetic, and ferromagnetic. You can see this little table there showing you which is which. Please don't concern yourself too much with this chromium saying anti-ferromagnetic. We're going to treat that as paramagnetic. We don't need to get into that business in IB. Each type responds differently when placed in an external magnetic field. In the transition metals and transitional metal complexes, the presence of unpaired electrons contributes to the magnetic field. Diamagnetic substances, electrons are mostly all paired. A good example is zinc. So what happens when the substance is placed in an external magnetic field? Well, initially there's no magnetic moment in the absence of an applied magnetic field due to pairing of electrons in orbitals. So there's no, because they're all paired, there's no magnetic force produced by the paired electrons. If you add a magnetic field to a diamagnetic material, in the presence of the magnetic field, a very weak opposition is produced, so that there is a very weak repulsion. Okay, a weak opposition is produced. If you then remove the external field, the atoms revert to their normal state. That's diamagnetic. Let's look at paramagnetic. Paramagnetic substances have unpaired electrons present. So what happens when the substance is placed in an external magnetic field? Well, the magnetic moment due to unpaired electrons are not aligned in the absence of an external magnetic, so it's not magnetic. You can see they're just kind of randomly pointing this way and that. When you add a magnetic field, the magnetic moments align with the field and the material is magnetic. Okay, so they align with the magnetic field this time. If the external field is removed, the magnetic moments are not aligned and the material is no longer magnetic. And finally, ferromagnetic substances. This is a permanent type of magnetism and is shown by iron, nickel and cobalt. That's right, only iron, nickel and cobalt. They all have unpaired d electrons. Okay, and I'm sure you can show how. Magnetic moments of groups of atoms within these materials are aligned to form domains, and the material is magnetic. So you've just got groups of atoms within the materials that are all aligned, and so the spinning electrons within the atoms kind of are pointing in the same direction, for want of a better word, and the little domains are magnetic. If you put it within the presence of an external magnetic field, all the domains are aligned in the same direction in the presence of an external field, and it produces an even greater effect, so it becomes more magnetic, or the magnetic field becomes stronger. You can test for diamagnetism and paramagnetism with this following setup. You get electronic balance and you hang a mass on the other side. And you put the sample you want to look at in a glass tube and hang it between an electromagnet, which provides a magnetic field. Okay. In a paramagnetic sample, a paramagnetic sample will be attracted to the magnet, so the mass of it will increase. A diamagnetic sample is repelled by the magnet, so the mass decreases. So you can see which is which. Okay, have a go at these questions. Okay, which element would be expected to be paramagnetic? You need to know which one has unpaired electrons first of all. And manganese does there. It's got these 5 unpaired electrons. Next, which element is the most paramagnetic? So we've got, these are paired. Now we've got 2 unpaired here. You've got 3 unpaired here, 1 unpaired. But this one has an almighty number of 6 unpaired, because the most paramagnetic. And finally, explain why manganese or zinc would be attracted or repelled by a magnetic field. Why the ions? Well, manganese has unpaired electrons, so it'll be paramagnetic, and paramagnetic substances are attracted by a magnetic field. Conversely, zinc has no unpaired electrons, so it'll be diamagnetic, which means it will be repelled by a magnetic field.